Good morning, everybody. Welcome to the Taiwan Semiconductor webinar. We have two, we think, exciting new product releases. We increased our product portfolio on ESD protection, and we also introduced our first shielded gate MOSFETs. So we'd like to give you a little bit more information about this. The first part is about ESD protection. We're going to talk about the ESD market and low capacitance, what it means, what is capacitance here. We have a product portfolio. We just like to pick up a few products there that are high runners here to tell them why we think they are special. And then our new products use Tyrista Technology or SCR in fallback technology. So we're going to explain or talk to you a little bit more about this subject. And we're going to look at one data sheet in particular, just to get a feel of what is in actually an ESD protection data sheet. The second part of the presentation is about MOSFETs. We're going to give a MOSFET. This is a little bit more commercial here. I think we got some good news that some of these new products are actually available. So we also want to talk to give you a commercial update about that. We're obviously going to talk a little bit about the market, about the technology, and then about which products we have released, which products are imminent in the next couple of weeks, we can sample already, and where we have capacitance. And then we're going to actually show you some benchmarking so that you get a feeling about how our products compare to the big market players like Infineon or Nexperia or people like that. So that's actually what we're trying to achieve today in our webinar, to update you about some of the exciting new things we're doing to expand our market. Or our served available market, I should say. Let's talk a little bit about the ESD history here. I always like to relax a little bit here and talk about the history and the market here. TVS, transient voltage suppressor. Actually, this is a market now about $1.7, $1.8 billion last year. So it's actually not small. You know, when we started 30 years ago, the older people here, we had these printers with these very slow interfaces, and if they needed ESD protection, we used to take TVS diodes here. But the data line speeds grow. We're trying to transfer more and more data, and of course do that faster and faster. So this capacitance of this TVS actually became a nuisance. So the discretes and these old products we were making were not particularly optimal. Also, the working voltage went down. So then the GPP stands for glass passivated pellet. That's one of the acronyms we use here, rectifying people every day, but that's what it means. So that's how we make them, and that was the old process for TVS. And but actually, planar and CMOS processes became better at moving from EDS. So the older TVS players kind of moved out of the ESD market, and it became a new set of competitors and a new set of technology here. In the meantime, however, ESD became bigger than the TVS market because we have all these interfaces, and actually you're more likely to have damage because of ESD than you have of lightning strikes or other high voltage events here, because we have all these fine lithography ICs where it's easy to melt the silicon and the metallization of the part. So what happens is actually ESD became one of the more costly ways to cause failures in circuits. So capacitance over the years became the driving factor of this industry. So what is capacitance? And we're going to talk about questions a little bit later on. First, we're going to look at these ICs, the Esd Wave Form and that type of stuff. There are many. This is the IEC one. There are a few other ones depending which regions you are. And the first thing I would like to notice, is this the x-axis, the scale there. So we're talking about something that is 100 nanoseconds long. So a very short pulse. So very little energy here. So if we then go on the left-hand side, what is important, I'm going to go from the bottom to the top. Robustness or surge levels, that's actually easy. The smaller the pulse, the smaller the die, the less silicon you need to spend actually to protect against it. So this is actually the easiest bit. Small die, and it's easy to do. Complexity, cost and supply chain, some of these things are glorified Zeners with expensive test programs or more complex test programs. That, of course, does not have any complexity, but the ones, once you see the capacitance is going down to a couple of picofarad, actually are, your complex products to manufacture. So there are not things you can knock out of your wafer fab in 2 weeks. Actually, behind some of these ESD products is a complex supply chain. The next thing, of course, is clamping, right? You need to protect the IC, usually the IC behind it, so the clamping voltage needs to be low. Yeah, there are things we can do with our products here, and this is important, but the most important thing in this case is also the layout. So it's the cooperating between what we do with the packaging people and supplying the package, and the way you do your layout. Signal integrity is on the top of the list of problems here, capacitance here, because you can protect a power line, and there the capacitance doesn't really harm you and that type of stuff. But if you're transferring data with hundreds of megabits per second and that type of stuff, and there is some capacitance on the line, the signal integrity becomes low. With signal integrity, I mean something like, imagine a signal, a 0 1s all the time, going from 0 to 1, and the 1 not looking like a 1, but being a little bit rounded in the corner here, because the capacitance isn't, makes it no longer a square. And after a while, if the capacitance becomes too much, then the 1 doesn't look like a 1 anymore and doesn't get recognized anymore. So that's what we mean by signal integrity, and that's what capacitance does to signal integrity. Capacitance here, the next slide here is just a brief overview of capacitance here. The drawing you see on the left hand side, here it's either with air or with any material, it doesn't matter here. So the capacitance is a bunch of material constants, the permittivity here, and multiplied by A over D. What is A over D in a semiconductor? A is the die size. So the bigger the die, the larger the capacitance. So we know the ESD pulses have low energy, so a small die size can handle them. So over the years, we have been trying to shrink the die size to making it as small as possible. So that's the number one thing that actually influence the capacitance. The second thing is the D, and the D in the semiconductor is the depletion layer. So what you're seeing on the plus and minus, or the P and the N, between there is a depletion layer, and if you reverse bias, that actually handles the voltage. So if you put 100 volts on or 10 volts on, that is determined, with the material, that determines the thickness of the die. What happens is, if you go to a higher voltage, the die actually, or the distance between the P and the N actually becomes larger. So if the D becomes larger, the capacitance becomes smaller. So that's what you actually see here, the capacitance going down with voltage. If you look on the right-hand side of your slide here, and you see the 1K SMB, which is a 1 kilowatt SMB TVS here, a package here. So what you see, the bottom curve here, you look at the x-axis, which is the breakdown voltage. So that's from 10 to 100 volts. This series goes from 10 to 100 volts. So what this does is, actually the bottom curves, there's a 10 volt part, of course, has a higher capacitance than a 100 volt part, because actually, this depletion layer is going up. So we're talking about here 1,000 picofarad, which is huge, which distorts any signal. So you can't use this on a data line. The top line here, the best way is to use the y-axis on the go to the y-axis on the right-hand side. So on the right-hand side, on the y-axis, you see 100 volts. If you actually put this 100 volts diode and reverse bias it with 100 volts, you get this capacitance of, let's say, 80 picofarad in that area. If you reduce the voltage, again, the depletion layer goes down and the capacitance goes up, and you end up with 500 picofarad in that area of capacitance. So this, tells you all you need to know about capacitance of a semiconductor junction. You can use it maybe also in other applications or other parts in your life. The second part, of course, of capacitance is you put two in series. The formula to put two in series is there, 1 divided over CT. The T stands here for total, is 1 over C1 plus 1 over C2. So what happens is if you, the total capacitance is always a little bit smaller than the smallest capacitance. So what you do here is you put a diode in forward direction in series with this reverse bias, the TVS diode, to get actually the capacitance down. So that is what you are, that's the trick we're doing, and that's the bottom circuit on the left-hand side. Just shows you, let's say the top there is plus and the bottom there is ground. In that case, the current will go through the right-hand, on the right-hand side, top diode, through the TVS diode, and then on the bottom left-hand side will go to the ground. If it's a negative pulse, it just goes the other way around. So this is the trick we're using. Put a low capacitance in series of the TVS to get there. There's also here on the top left-hand side, if you look at that drawing or that circuit, actually what happens is you have two data lines here where the capacitance is very important, where the signal integrity is very important, and then you have the V-bus, which can be anything, but in many cases is just a power transfer, a 5-volt line or whatever. In that case, the capacitance is not so important. So you have to distinguish if you're protecting between a data line, where capacitance is important, and the power lines where the capacitance is maybe not so important. So these data lines are, the low C products are made with complex CMOS processes. Don't underestimate them. They're no longer Zeners. It's a complex thing to make here. They're still small die, but they're still very complex to make. A lot of data lines are multiples of 2 or 4. So that actually here you see you try to put 2 data lines in one packages to save space. You can also do 4. So that's the trick we're using here. So what you have, of course, different interfaces can have a different maximum capacitance, but it never hurts to have a low capacitance, even on if you have an interface that can handle a little bit higher capacitance. So for us, the trick is how do we make with a few die protect everything in the industry here, and that's what we're actually doing here, and that's what I would try to show you in our product overview here, which is on the next slide here. This is taken from, you can do the same thing if you go to our website, click on ESD protection, and then, transport it out into an Excel, and this is what you get. I just made the file a little bit easier by picking out what is relevant and important in this case. So you can see if you go to the right-hand side, the number of channels. So that tells you how many channels, data lines the thing protects. And then next to that is the capacitance, the maximum capacitance here. Here you'll see that you can easily see the products being split into 0.4, 0.21. That's the capacitance typically for a data line. 9 picofarad, 45 picofarad, that type of stuff. That is capacitance for typically the V-bus or the power supply line can easily handle that. So the low capacitance products are essentially for the data lines. The high capacitance products are for the V-bus lines, and they usually come in 1, and the low capacitance come in either multiples of 2, 1, 2, or 4, depending on how much what the product line is. And of course, you need a number of things. Most of these data lines work either on 3.3 or 5 volts. The V-bus line here could be also up to 24 volts, depending on the application here. That is also possible, or that is a potential here for high current lines, and just also not data lines being protected. Here we go. We're going to go through a couple of runners, and then we can see a little bit what is important or not important on this line here. I'm going to go not in too much details here because it becomes a little bit boring if we go through tens of data sheet here. But first and for all, let's highlight here 2 or 3 things in the first package here. So the first is the package, the DFN 1006 here. So this is a perfect package here because it's small. It's a 1 millimeter by 0.6 millimeter and only 0.5 millimeter high. So it doesn't take out that much space up to protect against the data line. 2 picofarad is okay for the old standards. Usually if you go to the data sheets, you can see high-speed data lines, in this case USB 2. So it's perfect here for that type of application. there is the surges are very small and low, but there are various levels of ESD, which you see in the first line of the features part of this slide here. So features, that's 4-2, which stands for ESD, and then you have 15 kilovolt air and 8 kilovolt contact. That is the most common standard here in Europe. There are many other standards worldwide, and of course there are other levels of protection too, but that is just the most common one that most people have to protect with. Sometimes even you have to protect against less ESD damage here. So this is actually even on the safe side. So that's the one high runner we had in the past, and that's just a multiple line 2 picofarad you can use everywhere. The following thing, I'm not going to go through this data sheet in detail, but that's an existing product here on SOL23-6 with 6 leads. If you see 4 lines usually here and the combination of 0.6 picofarad here, you're usually talking about also HDMI and USB, apart from the applications there listed here. We'll talk a little bit more about that. So the SOT23-6 was the favorite package or one of the favorite package in the parts, but because it have leads, it has an inductance here, and that is critical to understand. So that does not help the overall clamping voltage, and I'll explain that to you later on why the industry, this is an older package, but it's maybe slightly moving away from this package to, for example, this package here, which is again leadless here. This is 2.5 by 1 millimeter here, also low profile, and it has 4 lines here and also protects against the ESD here. You can see 17 kilovolt and 12 kilovolt contact, so it's above the average norm or requirement of the norm here. And you can see also this one already is doing or protecting against high-speed interfaces in this case here. On the layout also, you have the IR pins on one side of the package here, and that is just for improving the layout. So these are the key packages here, and these norms, and so you can combine 1, 2, or 4 devices in one package here to data lines to increase density on the PCB. 2 new ones we've done here. This is an SOD323 package here, and actually what you see here, this one can do 30 kilovolts. Obviously you get a copy of this presentation here. This can handle anything, so 30 kilovolts air and contact. If you get 30 kilovolts in your body, you actually feel it. So this is some of the heavier pulses here. We're also here including here, and you can also ask some more information about that. Also some cross-surfacing. And the first slide actually gives you some of the key people here: Semtech, Borns, Diodes Inc., and Xperia. Later on, I think we'll also have TI. So there's quite a few people actually out there doing these type of products. But it's a big market, so it's interesting for us to also participate in. SOD323. This, of course, is meant for the bus line. This is going not just on a bus line, but actually any 5-volt line where there is a power transferred. You can add this to that line here. The other one here is when you put the DFN 106 here. That's the picture we showed up before here. So if you took 2 packages in this small or 2 lines in this small package, of course you can actually save port space. So that is the key thing here. 1 by 0.6 millimeter line, a package, you can actually protect 2 lines here. Important here to see when you benchmark also here, it is 0.65 picofarad capacitance here. What this capacitance does, sometimes, let's say in a USB 2, maybe that doesn't show up here. Also the 9.95 picofarad or 1 picofarad of the competitors doesn't show up. But as the thing goes faster and faster, you'll see that actually the capacitance becomes more and more important. So with one product with low capacitance, you can actually here cover the whole market. You see also we have a clamping voltage that's somewhere in the middle of the slide in the top here that is actually slightly lower. So that means actually we have a very good dynamic resistance, and I'm going to talk a little bit later about that too. So applications here and are clearly explained here. Now, what we're going here, and these are two products we're doing new here, this is the same package. We've shown you the one on the left before. That's the one we went to before. And on the right hand, we see a new product we are making here. And this is technology is called Tyrista Technology. Unfortunately, TLP stands for transmission line curve. That's figure 3 on the left and figure 5 on the right hand side. So that means actually it's the same as a TVS curve. You know, that if you go on the left hand side, you know, it's a 5-volt part. At 6 or 7 volts it starts to conduct, and then it's a resistance here, and it follows the higher current you shoot through it, the higher the clamping voltage here, similar to a TVS. So, you know, in the end, it clamps, let's say here at 5 amp or something like that. You know, the clamping voltage also already goes up quite a bit, or 10 amp. Those are the maximum currents you get in ESD. You get actually a significantly higher voltage, which may be higher than the CMOS voltage of the part you're trying to protect. So if it becomes over, then actually you're becoming in a gray zone. You know, they have some ESD protection on board. Will it fail? Will it not fail? You have to test and that type of stuff. So there is a small problem here. So what we're doing now on the right hand side is we're making the thyristor. So this actually, you know, the scales on the y-axis on the current is a bit high on the current, so you don't really see what happens at a low current, but it is actually functions as a typical thyristor here. So what happens is it's 3.3 volt is the working voltage. That means there is no leakage current or minimal leakage current at 3.3 volts. Then the ESD event happens, you know, 15 kilovolts or whatever, the voltage goes up, and then somewhere between 9 and 12 volt, you follow the x-axis to the right here, all of a sudden it breaks down and it goes down to a lower voltage here. So, and then, you know, that lower voltage, of course, is beneficial. It gives you a lower clamping voltage here. So this is a feature here which reduces the clamping voltage. What it also does here, it's not so spectacular in this case, but, you know, we also use this technology in thyristors. So what it also does actually is reduce the die size. And if you can reduce the die size because the clamping voltage is lower, so the power dissipation is lower, you know, of course, can again reduce the capacitance. So this is where you get the best results here. You can get a 0.828 picofarad. So that actually is good enough for any, or not for antenna, but any other any potential interface you can think of. You can protect it with this device here. So here we have the device that can protect anything here and will not have any distortion of the signal here. Important also, one differentiating factor is the dynamic resistance of 0.4 ohm here, which is actually gives you a very low clamping voltage also here. So that is a new technology which we introduced. This is the same part we just showed you, the data sheet on the right-hand side, together with cross-reference information here. Littelfuse is another player in this field, and the way it looks like from a layout perspective here. So, and of course also the interfaces here, which it does. We have two more of these parts here for other applications. The other one is on a single line. It does 0.5 picofarad. So anytime you, and the package is the 1 millimeter by 0.6 in this case. So anytime you have a single line with a 5 volt working voltage and you need a really low clamping voltage, you'll see here the clamping voltage is 5.5 volts and capacitance is 0.5 picofarad. You'll see actually here that we can also offer very good protection here. And the last one we're doing is a very small one, 0.6, 0.3 package here for data lines or anything here that's out there that can handle a higher capacitance here with 12 picofarad. So those are some of our new products. So we're actually expanding our product line here, and I showed you the overview. So I think we can offer a solutions for virtually everything or any interface on the market here. We'll look a little bit more at differentiating factors and packages later on. So what we're seeing here, if you're looking at a datasheet analysis here, I hope it's not too small on your screen. I look at these things every day, so I hope you're not overwhelmed by this here. So I took one of them. That was the last one we showed last time there, the DFN 0603, 2 lines here. with high speed. So what usually the datasheet has the application information, so for which interfaces it's suitable here, and also it tells you the maximum or the ESD against it protection here. Against it provides protection. So the IEC norm is contact discharge and air discharge are clearly highlighted here. So what is unique about this type of data sheet, if you go to the electrical specifications and you scroll down, working voltage, breakdown voltage, it's the same as a TVS, no difference. Forward voltage the same, leakage current the same, clamping voltage, that's where there is a slight difference here. We characterize the clamping voltage at 820 microsecond pulses. The reason for that is very simple. Actually, you cannot test according to ESD in a factory. The ESD pulse is not repetitive for outgoing testing. So we reuse the lightning strike pulse here to do outgoing testing on 820, and that's how we determine the clamping voltage. Of course, it will look significantly different on when you apply ESD pulses to it. They're much shorter. The junction capacitance, the one that is important is to the ground, in this case the first one here to pin 3. The ones in between them actually is just sometimes also important for some designers. The dynamic resistance, the lower the better here. It's one of our differentiating features on which we have actually a lot of presentation materials available. The next slide here is we're starting to the end of this. Here we're going to have to talk about layout and the entire environment. So if you look at our ESD pulse here, the left one is here the 820 pulse, how we test the device. The ESD pulse is what really happens. It's much shorter, but what really is the killer here is that you're having ESD currents of 5 or 10 amp, and you actually reach them within 1 nanosecond. So your DI/dt, your changes of current over time, is 10 amps per nanosecond. Some of you from school may remember the formula that the voltage is the inductance multiplied by the IDT. So normally we actually ignore this in the industry here because the inductance is like in the nanohenries, things like that. But here you have 10 to the 9 canceled by 10 to the 9th. So all of a sudden, you know, every millimeter on the board is a nanohenry, so roughly on a PCB. The bond wires here. So all of a sudden, this inductance becomes important because it creates extra voltages here. So that actually is a really key factor to understand also for package design and layout design. The graphs, I'm going to skip the graphs on the left because they're similar to TVS graphs here. Every graph here or every device here has a transmission line pulse here. That is an effective way to measure here to what happens under ESD. It looks like a TVS pulse, but it's actually relevant in the area of 200 nanoseconds here. What happens with the ESD event, usually there's a short overpulse determined by the inductance, and then it starts following the TLP curve here on your protection. But this is essential information now that you need to include in your data sheet of your TVS device. So finally, we're going to do product positioning on the ESD. Where do you stand? We have a number of die, 15 or so, that can cover most popular interfaces. Best for you to design in here. So if you have an interface and you need help on it, you know, we can usually offer a solution there, whether it's a USB, HDMI, or Express, or any other interface here. We can probably offer a solution here. What happens is in the market here is there is package proliferation out there. The ESD market started to come from 15 years ago, 20 years ago. People have older packages and then they moved on to newer packages and newer packages. So we have 15 to 20 parts names, and other suppliers sometimes have 200 part names. That includes a lot of older packages. Actually, we also have 15 part names that are not recommended for new designs and are actually obsolete. And those tend to be older packages or packages with gold plating and things that are not particularly practical here. We have a few packages that are moving, that are actually in the roadmap, like SOD 523. I would in general say if you split the market here on the data lines, actually on the data lines here, the inductance is less critical here, but the inductance is super critical. On the V bus or the power lines, the inductance is not super critical, but the inductance is very critical on all the data lines. So that's where the layout, every nanohenry, every inductance of the package becomes important, and that's why you also see those leadless packages here, because they don't have bond wires inside them. So that actually reduces your inductance a little bit here, and so those packages are going to be favored, and the industry is moving to those packages. And I think we have, with DFN 1006 and the other ones, we're actually have a lot of packages available for the future. Your application support is available here, and we also have good internal resistance as a differentiating factor, and we have presentations to back that up here. So that just gives you an overview of our ESD products here. I'll skip here. I forgot to mention this in the beginning. You can actually leave questions in the chat box, and after the presentation we'll try to answer them. Of course, it's a distribution seminar, so most of you have contacts within our organization, so you can just mail us directly if you want to do it in a more confidential way. But if you have general questions, please put them in the chat box, and it's difficult for me to read them, but Undine can read them out at the end of the meeting to answer any specific questions you have. And you can also, of course, just read through the materials for a second time and check out, I would like to have a little bit more information about that, because there's a lot of material about ESD, and this is an area where there is a lot of technical questions also sometimes by customers. The second part of the presentation is our new MOSFETs here, and I think this is also a big opportunity for everybody here, in a sense that there's not that many MOSFET suppliers around there, and I hope I can prove to you that we are actually committed, or very committed, to the MOSFET market, and can be not the biggest player in the market, but can be a substantial player in the market here. That's what we're trying to say here over the next couple of years. So it's not that we have a few MOSFETs here where we supply a few parts and that type of stuff. I think we're committed to this market and growing the business here. First and for all, this graph here is just some general market information. It's normalized on 2017, and it shows you the growth rate to 2021. The people here that know us, we know we're a rectifier company, and you can easily see that rectifiers grow around 30%. And that's good for us that the market grows, but we know all that there are markets that are growing a little bit faster here. Rectifiers roughly is a 4.3, 4.4 billion market, protection of 1.8, 1.7 here. Discretes, roughly, that's the yellow line, had the faster growth than rectifiers here. That's important to say. And the discrete market, actually, the global discrete market is around 30 billion. So it's not a small space we're playing in. It's actually a big arena. The reason why discretes are growing a little bit faster is because of the gray line, and one line that I didn't put in here. The gray line is the MOSFETs. Of course, they're growing a little bit faster than other parts of the discrete world. And the other parts that are also doing well are, of course, IGBT modules or IGBTs in general. So that's also a healthy line. And some wide band gap also has some, that's small business at the moment still, but also has very good growth rates. So that gives you a feeling here on the market sizes. And, we're talking about MOSFETs today. MOSFETs are growing well, and MOSFETs are now a $10 billion market here. So that's important to understand. It's not small business MOSFETs, and that does not even include the small single ones, like the 2 and 7002s and that type of stuff. That's another 700 or 800 million dollars here. So it's big business, and we want to participate in it. How do we participate in it? This slide comes from it's public information here from UMC. UMC is that's the bottom here in the red here. UMC finances from their finance report. UMC is a big Taiwanese foundry, and they are our partner and invested in our company. How does this foundry or how does working with a foundry look like on MOSFETs? First and for all, we're not unique. Infineon makes all their MOSFETs in-house, but
onsemi uses foundries, so does Vishay, ST, and Nexperia. So they all use foundries to a large extent here, to addition to their in-house manufacturing capacity. So it's not that we're doing something that is weird or nobody else doing. It's very common in Asia, but also actually the big OEMs in Europe actually do the same thing. What happens here? Let's look at the 2021 slide here. So what happens here, and we're going to go anti-clockwise here, and you're seeing the sales of UMC by photolithography. It starts at the top, you see 0.5 micrometer, and then it goes down the clock, and in the middle you see the orange part, 65 nanometers, and then it goes all the way down to 14 nanometers here. UMC is not the leading edge technology here, that's more TSMC, but this is just for medium complexity technology here. These people make millions of wafers every quarter here, and what happens is they see their customer base moving to more complex ICs, and they're seeing that their sales or capacity on things like 0.5 micron is slowly disappearing, or their usage of that is slowly disappearing, moving to higher end products, and then they want to fill it with something that can still use that technology here. And that's where MOSFETs come in. MOSFETs are designed usually, in the old days, it was 0.25, 0.35. We also had 0.5, but most people are at the moment 0.15, 0.18 micrometers. And, also 0.11, 0.13 is probably good for a future generation. So that's where we see that's 5% of UMC's capacity here, and that's growing. That capacity that they're using is usually for power management ICs and some digital stuff, and that's slowly going to smaller lithography features in that type of stuff, coming free for MOSFETs, and that's why we're interested here for them. Obviously they can get a better wafer price for analog ICs than they can for MOSFETs. That's why MOSFETs also are at the moment some of the components more complex to deliver here in the market. That is because they're competing against things that have higher margins here, but gradually that capacity becomes free and can be used for MOSFETs, and so we're getting quite a substantial capacity from UMC next year here, and so we can be a significant player with a huge foundry like that. So this explains you the business model behind our products here and why we think we can be a long-term player. And let's face it, as a distribution partner, there's not many people around anymore that make MOSFETs in the West, because there has been significant market consolidation with IR and Fairchild disappearing. The second thing is about technology. If people want to have a separate webinar on this, happy. I always like to talk about technology here, but we're not going to go into too much detail here. On the left-hand side is how a MOSFET is usually made. What you do is you see this green thing, which is the gate, or sorry, the polygate, the purple there, and you see these MOSFET signs. So you put millions and millions of these things in parallel here. You shrink the lithography here, go from 0.25 to 18, so you can put more and more in parallel. So they reduce the resistance here, but you hit the wall sometimes by increasing the capacitance, which then increases the switching losses. You don't want to do that. There are two things I'm going to mention on the left-hand side still in this slide before moving on to less technical stuff. Is this white arrow you see with X epi here. So what happens if you reverse the MOSFET drain source here, you make you reverse the voltage here, then the breakdown of the voltage is the electrical field is on this epi. So you need a certain material there or resistivity here, which increases the RDS(on) of the MOSFET here. So you want to reduce that here. So that's the number one thing you can do to reduce it. And the second thing you can do is make them thinner. So the substrate is also contributing to the overall reduction or the overall RDS(on). So there's all kinds of tricks you want to do to make them smaller, or to make the RDS(on) smaller without increasing the capacitance. And that's what the shielded gate trench do by having under the gate there, you see a second purple or blue or whatever color it is, here, that's the source here that will change the electrical field here and reduce the RDS ohm. So that's the trick we're using here. I'm not going to go into further details here, but we get ultra low RDS on. We get a bigger figure of merit because we're not introducing the capacitance here. We have a built-in RC snubber, which actually helps to eliminate spikes in here. QGD is a turn-on here, losses here that are better. And the QGD-QGS ratio is when you inadvertently turn on the MOSFET by changing the drain voltage. You want the gate to be as robust as possible. So there's lots of advantages here of this new technology here. And the best way to show that is here how the old way of turning on, that's the graph in the top right-hand side. The old way of turning them on, and the new shielded gate technology here is a fast way of turning them on. So it's the turn-on times are much faster. You can switch at higher frequency, and you have fewer losses here. So that's essentially what the split gate, shielded gate does. Split gate is another way. I sometimes mix them up. Shielded gate is a better way of doing it. It's a way you listen to it. So here we are. This is a good slide to share with customers here, to technical customers in technical discussions and things like that. So what you're seeing here on the left-hand side is on logic level MOSFETs. There's some TSC speak here. What you see when you see NB in the part name on the bottom here in this top left-hand graph here, that's the old part names, or that's the old technology. NH is the name for the new technology. What you see here is that the difference between in logic level between 10 volt and 4.5 volt has become much less here. So that's an advantage if you have logic level applications here. The QG and the QGD also has gone down. That is usually associated with faster switching and with lower switching losses. The one on the top hand right here is the threshold voltage is narrower. That is, it says better noise immunity. You can also more easily parallel devices here, so we're also gotten better in there. So those are the typical technical specs we're using here. The new parts here on the bottom right hand side, we don't have two packages anymore for the new parts. We're all using the automotive packages for the new series, which is called the side wet ball flank or wet ball flank, and that's the one with these funny U shapes in the protruding parts where you solder here. So we have only one package for this device here. The other thing we've improved, RDS-on has a positive temperature coefficient, and that is better with the new technology over the old technologies. So those are all features here which we can tell or talk to customers here, and which actually put us also in line, as we will see on the benchmarking later on in the presentation. This slide is actually summarizes it also, but it's a nice commercial slide. On the left-hand side, you see what we could be doing in the past here. Our past series, the NB series, the one we released in the past, was very good for BLDC motor control, it at 40 kilohertz and that type of stuff. If we want to go to applications that switch at 150, 200 kilohertz, we want to go to this new series. So we essentially, by also introducing these new parts, because you might say, oh, you had a 5 or 7 million part name and you have a new 7 million part name. What does it bring for us? Well, it's not only better technology, it also expands the market which we can address. So if you have distribution customers in BLDC motor control, you know, that was good for the old series. Now we can also go after power supply or DC-DC converter type of applications here, because if you look at the features here, the good figure of merit here reduces the switching loss. So we can work at a higher frequency. The rest are more or less a repeat of the old slide, but also just on line 4, RG stands for the gate resistance, and that is also a feature which is linked to the switching performance. And also here we've made improvements here to actually also service the market of these high performance power supplies. This is a list here you can have here. These are the parts we released last week. 1.9, 3.3, 5.6, and 7 milliohm. That's the second column. Logic level and standard level. So those are the parts that are available on the web here. And we also have a dual at 7.6, all 40 volts here. And, you know, parts are available, SPICE models, data sheets. We can sample them. and actually we can also ship them here. That's actually also a piece of key performance here that I hope will get you a little bit excited about our new product launch. Is capacity available, maybe not for all packages, and maybe it's not that fantastic here. So we are actually here, but that's also impacts our availability of products here in 2023. So where we're actually also investing internally here to increase our capacity. But what we're seeing here is that we have capacity available for Q4, especially on PDFN 3x3. We can actually ship 3 million per month. Obviously, this information is a snapshot from last year. You can imagine that we have a lot of salespeople and everybody is chasing this capacity. But you are one of the first to be informed here. You're doing the first webinar, so please notice that we can work together on these products here to ship in Q4, and I'll tell you a little bit more how we can do that at the moment here. The lead time here for MOSFETs here gives you an idea here. At the moment, this wafer fabrication lead time here, the acronyms you see, BGBM stands for back grinding, back metallization, CP stands for chip probing, and then you also have to cut the wafer. So that type of stuff, that's actually fairly normal here, 2.5 months or the 10 weeks in that area. So that's pretty normal, even in good days for MOSFETs. Maybe can do a bit faster, but that's not normal lead times for MOSFETs here. The assembly times are a little bit faster here. The cycle time is usually faster, but obviously there is a shortage in the back end, also lead frames in Taiwan on MOSFETs. So that's something we need to accomplish, to work with in that type of stuff. But we are working together still on shipments in Q4 for those products here, because some of those wafers are already have been started here, and there is some capacity available here. So the only thing you need to know in this case is, of course, we have the released products here, the 10 or 12 you have on the website where we can get orders here. But there's 8 more products which you can work together with. Obviously, here at this stage, we cannot open these products for engineering samples, so we need to know the projects and we need to be carefully involved in that type of stuff. We are talking about, products with existing die and packages, so the risks of qualification is low, but it's not zero. So we can always say that, we have engineering samples available now, and we are going to ship in July, and we might even confirm orders before July 2022. But obviously, if the qualification fails, it all falls through. So this is something we have to honestly mention here. The first 4 are just the extension or the 2 parts missing from the product lineup of the PDFN 5x6 package. So that is available 2.5 and 4.3 million parts. The second one are the ones where we have the most capacitance, the PDFN 3x3 packages, and those we have available in 5.6 and 7 million standard level and logic level here. So that's what we are, and just again in red here, PDFN 3x3 has the biggest immediate upside. So if you know somebody who has a 7 million project somewhere in PDFN 3x3, let us know, and we can see if we can try to go after that big business if possible here. We obviously will be working here with, and I'm showing you here, these are not available on the web. They would also only be shared if we know and understand the project, and the customer also knows what we are doing, so there is no misunderstanding anywhere. But we're working with preliminary data sheets, but those preliminary data sheets have been fairly well characterized. I don't think we'll have many changes here in those data anymore. So we've been measuring those data pretty significantly in the past, or on a few lots here. So what we're doing here, so that's our change. So that's here the message to you that we have on PDFN 3x3 potential short-term upside here in that type of stuff. We're actually also here cross-reference part. We add that to the handout, but obviously we all know it's against Nexperia and Infineon and Vishay and the usual suspects. onsemi, of course, also. So onsemi is causing a few problems in the market, and Alpha Omega also. We obviously are competing against them too. That's more Asian. We don't see them that much in Europe, but that's a big competitor in Asia, and there are a few Asian ones which you may not recognize here. The last thing here, so we're obviously working on a roadmap later on. We don't include that because that is confidential, but yeah, I think you have all the important information here, in the presentation here about things what are short-term upsides. Of course, we're working on 60 and 100 volts, and that's also exciting here, and we'll keep you updated, but that's more going to be more in Q4 this year. The packages are also, I should mention that, non-automotive at the moment. The automotive qualification is also scheduled for Q4. So those are two pieces of critical information which I also should mention here. The last bit is benchmarking here, where you see the competitor here is, in this case, is an Optimos 5 part from Infineon. So that's pretty much state-of-the-art technology here. We've done benchmarking in the DC converters and other applications here. Here we're benchmarking in a power supply with synchronous rectification here. So what you see, less platform, an LLC converter here with synchronous rectification. You have a 390 volt line, sorry. Output is 12 volt. On the right-hand side, you can also see it's a 40 amp output here, and you have a switching frequency here we're using of 150 kilohertz. So we put both the Infineon part and the part of Taiwan Semiconductor in the board. And what we're seeing here, this is a summary. I have more details on the part here, is that the efficiency of both parts, both at low load at 25% load, where at low load you may have a slightly higher percentage contribution of the switching losses. At 100% load, this thing is going to be 100% dominated by RDS(on). And so you see that the performance between both parts is on the top. You see the thermal performance of our part, the thermal performance of the Infineon part, which is copper clip. So that may explain part of the difference here, or the higher for them, but the junction temperature is going to be pretty similar here. And you see that the spikes caused by in both sides are also fairly similar to both devices here. So it's probably fair to say that our performance is similar between both devices, or between both parts names. So, and we have other, we can also share always if you need anything. We also have testing versus Nexperia and a few other onsemi and a few other components on the CDC conversion. So this is something we can share if customers want to get a better feeling here. We think we have leading edge technology here, and we can prove it via benchmarking. So thank you for your attention here. Any questions here? We're gonna, I think, open up the thing here. I think you will stay muted, but you can actually put your questions here in the questions button, which last time when we had it, I failed to see them. But Undine might find them or tell us all about it. But please tell us, also send them via email if you want to. I'll stop here and see if there are any questions. Undine, did you see any questions?
No, there aren't any questions.
All right, it's our distributor friends, so they can contact us any other way. In that case, I will close the webinar. You can follow up for the presentation with Undine, which of course there's nothing confidential in this webinar, so you can have all the slides. And in that case, I would like to thank you for your attention. And for most of you now, it will be the lunch break. So I think I wish you a good lunch and a pleasant afternoon. Thank you very much.